Hey guys, welcome back. I'm Andrew, and today we're going to be going over some u substitution to solve the integral, the definite integral. So we have here the integral from the lower bound of 1 to the upper bound of 2 being multiplied by x e to the 3x squared and the dx. So when using substitution, one of the things that we're going to always try to look for is, well, what's familiar to me and how can I substitute in? So I'm going to go over here, and you guys can do this in your notes for bookkeeping purposes, and let whatever function that you're using in here, or whatever you're trying to substitute, you want to distinguish that off to the side. So for my variable, I'm going to choose u. And I'm going to go and look over here, okay, what can I choose as my u? And so I'm going to have my 3x squared be my u. Now when doing substitution, you're going to want to take the derivative of this variable. So I'm going to use du, meaning I'm taking the derivative with respect to u here. Now I'm taking it with respect to x on this side. So I'm going to get 6x dx. But now I've got u's and I've got dx's, so I'm going to now write dx equals du over 6x. And then what I'm going to do is I'm going to plug in chug basically. I'm going to take the terms I have over here that I've set aside and put them back into the integral, where I've got now my definite integral, but we'll get to that in a sec, of x times e to the u, which I substituted in for my 3x. Now I've got my dx, and I see that I've got my du over 6x. The other thing you want to worry about is, well, do these upper and lower bounds carry over? And the answer is no. When I showed Lily this, she would put 1s and 2s for the upper and lower bounds, and that doesn't work. What you have to do is take those upper and lower bounds and plug them in to get your new values, because we're using a new term as our rate of change. So for my new u value, I'm going to have my lower bound 1. So I'm going to plug that in. We have 3 times 1 squared, which is going to give me my new lower bound for the definite integral as u equals 3. And now I'm going to do it for the upper bound, so I'm going to have u equaling 3 times 2 squared, just to make sure you guys follow along, and then we're going to get 12 as my new upper bound. Make sure that's the right color for you guys. And so now we have everything in terms that are related, where we've got u's for the upper and lower bounds, and we have u's in our definite integral. Now one of the things that we say, well, I've still got x's in there, but the great thing is I can take these two x's here, because one's in the top in the numerator and one's in the denominator, I can cancel them out. So now I have my definite integral from 3 to 12 in e to the u du. Now this looks so very familiar to us, just like when we started in the beginning. And I just forgot my 6 underneath there. But this looks very familiar to us because the integral from e to the u, or e to the Hello Kitty, or e to the x, is going to be e to that variable itself. So this looks very inviting to us whenever we solve these types of problems. So now, go over here to finish it, where I'm then going to take the derivative, the integral of e to the u, keeping this 1/6 constant because it's in the denominator. So we have the 1/6, then I've got my definite integral from e to the u, which equals e to the u again, which is very nice, and I'm very happy with it. And then we've got the upper and lower bounds that we're evaluating here. And in order to evaluate, we have to go and plug them in. So I'm going to go from an upper bound, subtract it by the lower bound. So I'm going to keep the e to the u, but instead of u, I'm plugging in the 12, which is my upper bound. Then I'm subtracting it by my e to the 3. And here we have our final answer. Whenever you're using substitution, you want to look for a problem that we're given. Say, okay, what can I do to change the problem to make it in a more familiar way, like we have here. I've got an e raised to something, but I'm multiplying it by a function. I'm going to take that in this part here, or in the exponential value, set that equal to my substitution, take the derivative, plug that stuff back in, and I see that we now cancel it out and we get into a more familiar term. Here, when I showed this to my friend Marshall, he said, well, why can't we just go ahead and just say, well, if I'm doing this integral and I get to this stage here, why don't I just write this as 1/6 e to the 12 minus 3, which then gets me to be here as my final answer. The reason for this and why this is incorrect for Marshall's way of thinking is whenever you're using exponents, if you're taking a product of the exponents like we showed earlier, where we had, going back to the 2 squared multiplied by the 2 cubed, because we're taking the product of them, we have 2 to the 5th. In Marshall's case here, in our case here, we can't add the exponents because we're now having a 2 squared plus a 2 cubed, which then equals itself. So if we're going to really expand this, here I get 32. When I expand this, I get a 4 plus 8, which equals 12. In these cases, both are correct, but for our case here, for the integral, we have to use the sum or the difference, because if we're graphing this exponential function, and the graph looks like this as it increases, and I've got my 3, and I have my 12. And anytime we're doing an integral, we're saying, hey, what's the area underneath this curve here between these 2 points, 3 and 2? What you're doing is saying, okay, if I'm just going from 0 to 12, for my lower bound, instead of it being 3, it's now 0, I'm taking the derivative of everything. But when we incorporate that lower bound as the 3, we're now subtracting out this section here as the checkerboard to leave with just the slash marks. So then we get our area underneath the curve there.
I have a question.
Yes, Bob, go ahead.
Why can't you let u equal e to the 3x squared? Does it matter?
It does matter, because if I just leave the if I just have u equal e to the 3x, then I'm still left with an x term. So let me just go ahead and do that. So if I just let u equal 3x, then my du equals 3 dx, and I plug it back in, I'm going to then have my x e to the u squared, and then I'm going to get du over 3. And this way, I can't really cancel out the x, so then that's why we have it to be the x squared. So we're foreshadowing how we go in the future to see, okay, what's the path that I'm taking? Is it to get stuck here, or do I need to include the squared term like we did here in the beginning? or I am still left with an x term in the denominator so that the x can cancel out. All right, thank you guys so much for taking the time to watch this, and I'll see you in the next video.